Hello there. Now we are trying to find out the moment of inertia for the circular lamina. So this is one of the regular objects widely using in our engineering application. Suppose you can take a shaft or you can take a gear blank or you can take any kind of the engineering objects. Most of the time they are going to be in the circular shape. So then we can take that automobile tires also, they are in the circular because the rolling capability is going to be much better compared to the other shapes of the objects. So now we are going to be finding the moment of inertia for this one. So it's not only the moment of inertia, we are trying to find out the polar moment of inertia we are going to be finding. So how to calculate the polar moment of inertia, that's we can see. So this is going to be the circle they have given, and then there is going to be a radius is going to be existed. From this O, I'm going to say this is the X and this is going to be the Y axis we do have. At the same time, the concentrated, that means the intersecting point, I'm going to be say the O where it is going to be the originating. So the radius is going to be the R we do have taken. At the same time, while you are doing the moment of inertia, so first we have to take the one elemental strip. On that basis elemental strip, we are going to be calculating the moment of inertia, and then we are going for the total moment of inertia we are going to be calculating. So in this case, I'm going to be taking the one elemental strip little away from the center of the circle. So for this one, I'm going to be taking the one elemental ring I'm going to be considering. So that elemental ring is going to be located. So this is going to be your elemental ring, that's I'm showing in the by the hatch, right? So in this case, what will happen? It is going to be located at a distance of small r, right? At the same time, the thickness of this elemental strip, I'm going to be saying the dr. So capital R is going to be the your total circle radius we do have taken, and small r is going to be the elemental strip radius. It is located at a distance of r we have taken. At the same time, the elemental strip thickness is going to be considered as the dr. So then how could you are going to be calculating the moment of inertia? So for this one, we are going to be taking the moment of inertia about the polar coordinates we are going to be considering. What is the polar coordination? What is the Cartesian coordination? As we know that x and y, if I am going to be taking, that is going to be your Cartesian coordinates. But if I am going to be taking r as well as the theta, then I can say that is going to be the polar coordinate system. So how could I take the polar coordinate system here? That's going to be the moment of inertia of a circular lamina about the axis of about the polar axis, right? So that polar axis, if I'm going to say that I'm going to be taking IP, I'm going to be calling the IP is going to be the designation with the polar moment of inertia. IP is equal to, what is that one IP? So that I'm going to be taking the elemental area into the radius square we are going to be taking. That's going to be located at a distance of r, it's going to be there. So then what is the elemental area, how we are going to be taking? Because the elemental area is going to be existed throughout the 360 degrees. So that elemental area I'm going to be writing 2 pi r into dr is going to be the thickness we are going to be multiplying, so that we will get the area of this elemental strip, and it is located at a distance of r square, it is there. So this is going to be the r square. Then finally, the elemental strip moment of inertia, polar moment of inertia, that is equal to 2 pi r cube dr we are getting. So this is only for the moment, the polar moment of inertia for the elemental strip. Now I need the polar moment of inertia for this total entire circular lamina, we need it. So then what I'm going to do, I'm going to be integrating with respect to the 0 to r, so that I'm going to be calculating the polar moment of inertia for this circle. So here we are going to be say the polar moment of inertia IP, that is equal to integral 0 to r, that's representing the total polar moment of inertia of the circle, that's going to be 2 pi r cube dr we are getting. So if I'm going to be integrating this one, in this case, which is the variable parameters, that is the r, and the dr is going to be the variable parameters. So then IP is equal to 2 pi into r to the power of 4 by 4 I am going to be getting. That's going to be 0 to r, I will get it, right? This is going to be 0 to r. So then IP is equal to, if I am going to be simplifying this equation, so then what I am going to be getting, the 2 will going to be cancelled, pi capital R to the power of 4 by 2 I will get it. So this is going to be the polar moment of inertia for this circular lamina. Right? So then how we are going to be calculating the Ixx and Iyy? So as for the definition, polar moment of inertia is equal to Ixx plus Iyy we are taking. Iyy. As we know that this is going to be existed, the symmetry is going to be existed here with respect to the Ixx, with respect to the Iyy. So then what I am going to be taking, so for the simplification, Ixx is equal to Iyy is equal to Ip by 2 I am going to be taking. On that basis, I am going to be calculating the Ixx, Iyy, that is equal to pi r to the power of 4 by 2 we are going to be getting. So that I am going to be taking pi r to the power of 4 by 2 into 2, that's going to be 4 we will get it. So this is going to be in terms of the radius. Suppose if you want to find out the polar moment of inertia or the moment of inertia with respect to the diameter. As we know that the diameter d is equal to 2 into r. Right? So then simply r is equal to, we are going to be calculating d by 2. If I am going to be substituting r is equal to d by 2, so then this pi into d to the power of 4 and this is going to be 2 is going to be multiplying with the 4 times. So then that 4 into this final value I am going to be writing here. So here I am substituting r is equal to d by 2. If I am going to be substituting the polar moment of inertia, that's Ip is equal to, what is the formula? Pi into d to the power of 4, and 4 into the 16 we are going to be getting here 32 we are going to be getting. So this way we are going to be calculating the polar moment of inertia. So now we are going to be taking the Ixx is equal to Iyy is equal to pi d to the power of 4 by 16 into 4 is going to be 64 we are going to be getting. So this way we are calculating the polar moment of inertia as well as the moment of inertia with respect to the Cartesian coordinates also we can calculate it. So after we calculated the parallel moment of inertia as well as the Ixx and Iy, that is going to be the moment of inertia we do have calculated, right? So now we are trying to concentrate on the other problem with the continuation of that. That's what is that one? The moment of inertia of a circular lamina. This is so far we have completed. Now we are going to be trying to see that with a centrally situated circular hole. In this case, what will happen? In the previously, there is a solid area is going to be there. That is going to be complete area of the circle is there. But in this case, there is a central hole is going to be existed. So there we can see the initially capital D is going to be the total circular area. That is going to total circular diameter. Sorry for that. And small d is going to be the whole diameter that he has given, and x coordinates as well as the y coordinates he has given. So now we need to find out the moment of inertia or polar moment of inertia for this one. So how we are going to be taking in this case, capital D already we know. So that I am going to be taking the total polar moment of inertia Ip is equal to Ip d capital D minus Ip small d I am going to be considering. That is the polar moment of inertia with respect to the outer diameter and polar moment of inertia with respect to the inner diameter. In this case, what will happen? It is going to be only the area is going to be existed between the small diameter as well as the big diameter. But inside there is no area is there. Then what I am going to do? I am going to be taking the entire area capital D minus small d Ip I am going to be taking. On that basis, I can calculate it. So how we are going to be calculating? IPD is equal to, we do have the formula 5 by 32 d to the power of 4 minus 5 by 32 small d to the power of 4. In this case, the common terminologies I am going to be taking out. That's going to be 5 by 32 is the common, capital D to the power of 4 minus small d to the power of 4 we are going to be taking. So then Ip is equal to, this way we are going to be calculating the polar moment of inertia. Similarly, Ixx and Iyy also we are going to be calculating. That's going to be Ixx is equal to Iy is equal to, what is the formula we do have? That's going to be 5 by 64. That's going to be capital D to the power of 4 minus small d to the power of 4. This way we are going to be calculating for the your Ixx as well as the Iyy. So this is the way we are going to be calculating. So the outcome, what we learn from this the lecture. So that means we are able to do, that means what we can do here, determine the polar moment of inertia of a circular lamina we are able to do. So that means polar moment of inertia as well as the moment of inertia also we can calculate it. So then calculate the polar moment of inertia of centrally situated circular hole. Suppose in this case, this is going to be the complete circle we do have, when there is going to be a hole is there, so that we are going to be calculating. And similarly, if the circle is going to be there and there is going to be that means, so there is going to be a square hole also there. So easily we can calculate the moment of inertia. Not only this one, there we can do irregular shapes also, we can able to calculate it. So thank you for your support. If you feel any query regarding this, the polar moment of inertia on the circle, then you can comment in the comment section. Thank you.